Okay, guys, we are continuing. I'm happy to welcome Alejandro Pedrosa on the stage. He's going to do the next talk on L2s Interoperability Landscape. He's a senior protocol researcher at Scroll. And yeah, going to hand the mic now to Alejandro. A big round of applause, please.
Okay, yeah, it works. Cool, thank you. So I'm Alejandro Ranchal Pedrosa, and I'm going to be talking about interoperability landscape, or L2s. So here's a bit of quick outline of the presentation. First, why interrupts, why interrupts. So I want to spend some time talking about decentralization, and I will justify why I talk about decentralization when I'm talking about interrupts. General goals that we want to have, ideally for this kind of like one of the things that we started with at Scroll, that what is the perfect solution, right? And what are the goals that we want to like uphold while we are talking about interrupts and what we provide as a solution for interrupts. And then we went out to the space, try to like find the high level fundamental solutions and the trade-offs. And so there's like 3 main trade-offs I want to talk about. And finally, where do we go from here? Yeah, okay, thank you. Hopefully, should I start over? Was it heard? Okay, well, I'm gonna assume that you heard what I was talking about. Anyways, it was the outline, so you catch up. Yeah, that's not ideal, but okay, that is not that big of a deal. Anyways, so yeah, what is interrupts? So interrupts are just 2 rollups performing some state transition that depend on each other, right? And fundamentally, you have 2 distinctions. There's one that is easier, so it's just token transfers. The reason why it's easier is because you don't care, because there's fungibility, so you don't care about getting the exact same coin. You just want to get a coin of that currency, right? And then there's general state. General state is also equals to, let's say, you can also think of token transfers, but there's no liquidity. Nobody wants to give you liquidity, so you actually have to wait for the actual coin that this other person is giving to you. But also some other things, like NFTs or some other general state. It's like calling a contract in some other rollup. This is something that's very easy to do in L1 because you just submit a transaction and you make the payment, or you have like a call to a smart contract that might or might not call some other smart contract. In L1, this can be performed atomically, right? And the gas, you can check on the gas, and the transaction can be valid or not, depending on that. But in the case of different states, you might execute the first transaction, but then that one, ends with a call to some other transaction, some other rollup that has a different state, and there's not enough gas, for example, or that other rollup is not live, so the transaction doesn't finish. So what do you do with this like partial state transition, sort of? And also, who's gonna be, somebody has to relay this information. How do you incentivize that? How do you make sure this is safe? So there's a bunch of questions that arise when you're dealing with different states for interrupts. Wait. Okay. Yeah, so why do I want to talk about decentralization when you talk about interrupts? Well, rollups have a shared layer, a common layer, which is L1, right? So you can always do interrupts through L1. But that means paying the cost of going to L1, both in terms of fees and in terms of latency, which is prohibitively expensive for many applications. You don't want to wait. You just simply don't want to wait 12. And it's not even going to be 12 seconds. It's not going to be a slot. It's going to be finalization, right? Because in many cases, it's going to be finalization. So a rollup is not going to react to a state transition in another rollup. Hello? Okay. A rollup is not going to react to a state transition in another rollup unless it's guaranteed that the other rollup finalize that state transition, if this is done in a completely trustless manner, right? But yeah, 12 minutes is, so the finality time. Ethereum is probably just too high for many applications, and so now we have to make compromises. So we have to find a way to do interrupts at faster than Ethereum latency. And to do that, that immediately means you're going to need to trust something else, because there's always a possibility that the other rollup might try to cheat on you and just go and submit a different state transition than the one that it gave to you, right? So some equivocation attack, some non-safety attack. So you either need to trust this other rollup and any other rollup that you interact with, or you need to trust some other intermediary. But there's going to be a need for trust, and we're in the space of trusted stuff, and this is critical, especially when you deal with general state, because if there is a state transition that gets reverted that you depend on, then this is undefined behavior for your rollup, so there's not even a well-defined way to go forward. For the token part, it's different, but I'll talk about it. So it's critical to have a solution that, a valid solution for general state interrupts is going to be very tightly connected with a solution that is decentralized. Okay. Yeah, so now we went into some high-level requirements. I already justified decentralization, but we also want a solution that is horizontally scalable, right? That scales very gracefully with the number of rollups increasing and more interrupts being demanded across rollups. Security, you could argue decentralization is part of that, but in general, trust minimization on chains and layers other than oneself. And also UX friendliness, right? Like the experience in L1 is very simple for multiple contracts calling each other. It's just one transaction, and we want to have as close as possible to that experience. So the user doesn't need to worry about anything, or even the developer shouldn't have to worry too much or at all about anything other than I just build my app. And if my app depends on some other contract that is in some other rollup, that should not be my problem. Maybe I have to pay more, a little bit or whatever, but I shouldn't have to worry about some edge cases of what can happen between rollups interacting. But of course, the ideal solution, we're far from there. So then, as I said, we went into the space of existing solutions, and we identified one fundamental philosophical difference between the space of solutions. One is what I call, what we're colloquially calling the hub and the mesh. And I've also been calling it from the perspective of a rollup, a custodial, so a rollup that interrupts in a custodial way or in a non-custodial way. So the hub, or when rollups become non-custodial, basically means that a hub becomes this shared layer, so you only need to trust this shared layer in order to perform interrupts, which means that I don't even care about the other rollup and what the other rollup might do, because I don't even trust it. I only trust the shared layer that is the same dependency for all my interrupts. And the other one is the mesh solution, where any interrupt I do with any rollup, I need to trust this other rollup. So this other rollup becomes a direct dependency of my state transition. And if this other rollup behaves badly, then I have to deal with that. But let's go a bit more into detail. So let's start with the mesh. The reason why I didn't just give the colloquial name of mesh is not because there is a shared layer does it mean that is a hub type of solution. So, and I put it specifically Arc layer as an example, because Polygon Arc layer is a shared layer so everybody is going to be looking at that layer in order to perform interrupts. But still, the problem is, the reason why it's still a mesh type of solution, according to this terminology, is that in this example, where we have rollup A and some state in rollup C that is triggered by a state transition that happened in rollup A. So in this example, some NFT that has been transferred to some user in C, in rollup C. So there is a state transition in C after it has seen, so the state transition happens in A, that includes this transaction that transfers an NFT to C. Arc layer sees this state transition, says, yeah, I've seen this happened. So C only looks at Arc layer and says, okay, Arc layer said it happened, I trust Arc layer, so I'm gonna react to it. In this, if doing this with Arc layer means that if rollup A is malicious, rollup A can still equivocate. It can submit a different state transition that actually transfers the NFT to someone else in A. And now rollup C actually has to revert. This is what Polygon Arc layer says is not a safety issue. It says it's a liveness issue. Because the argument is rollup C can revert, and then it's going to be able to settle again on Ethereum. I think we should be very clear on the dependencies and the risks involved in these kind of solutions. And to me, this is a safety issue, because some user in C thought that it received the NFT, and maybe reacted to it, it gave back, I don't know, a car or whatever in the real life, and now this gets reverted. And it's not because the rollup that this user participated in was malicious, it's because some other rollup was malicious. So, so this is what I call a mesh solution. So any interrupts that happens in a mesh solution with any other rollup, you need to trust that other rollup. So this scales, with the more dependencies you have, as soon as one of them is malicious, your state is inconsistent. And these are examples of projects that are going in this direction. So AgLayer, Optimism Superchain, and Arbitrum, I forgot how it's called. I think it's clusters or something like that. But yeah, it's the same fundamental solution. Then there is the hub. Now the hub is not perfect either. There's also a trade-off there. Okay, I would love to see it here as well. I don't know what. Okay, well, so the hub. Okay, there you go. The hub is the good thing about the hub is that you do not need to trust this other rollup. So what happened before, the example I put before, where A creates a state transition that integrates this transaction, and then C reacts to it, and then A tries to equivocate, go into Ethereum, and submitting a different state transition. This is not possible. How is it that it's not possible? Because in the fast path, any state transition that is submitted by A to Ethereum needs to be approved by the hub. So it needs to be it needs to have the hub seal of approval. So for that to happen, for that previous attack to happen in the hub will actually need to also equivocate and seal, approve this other state transition that they is submitting to Ethereum. This is in the fast path, of course, because the other issue that arises with the hub is that if the hub is non-live, so if the hub goes offline, A is not going to be able to submit anything to Ethereum or anything that it has done recently because it's not approved by the hub. This is solved by a slow path. So after some period of time that we assume is enough time, so A can basically submit the same thing as forced inclusions, forced batches, right? So rollup A can say, hey, the hub is offline, so I'm going to go to Ethereum. This is my latest state, and Ethereum says, all right, fine. Let's wait for a bit of time to give time to the hub to challenge this state transition, and if the hub doesn't do it after X amount of time, you're good to go, and now you're out of the hub as well. So that's kind of like the trade-off. Also, I forgot to say, in the mesh solution, one way to go around it is to just wait for the submission of A to Ethereum, or whatever state transition. But in many cases, that's going to kind of fail the purpose of the interrupt solution because we're trying to solve faster than Ethereum latency. Right, so you're gonna need to depend on safety in the mesh, whereas in here you're depending on liveness, but you depend on liveness once. There's no but yeah, that's one disadvantage of the hub. Okay, and the examples of solutions that have the hub. So sequencing is going in this direction. Espresso is going in this direction. We have another case with Espresso similar to Polygon AgLayer where probably they don't like to speak of a safety issue, so they call a liveness issue, and they find some convoluted way of justifying that. In Espresso, they don't like to talk about this dependency that becoming the hub means to the users, to other rollups that are joining the hub. So they try to hide it, but essentially, and I know this because I asked them directly, essentially, if you join Espresso as a rollup, and even if you don't do any interrupts with anybody, just by the sheer fact that you joined the Espresso, if after joining you want to submit a state transition to Ethereum, you need Espresso's seal of approval in the fast path. So yeah, that's kind of the trade-off the fundamental trade-off that exists when operating a fast and Ethereum latency. And it's not surprised because this also exists in L1s. So you have, put differently, so rollups actually now, if they want to do completely risk-free interrupts, they go through Ethereum. So Ethereum is the hub. Right, it's an inherent hub for any rollup. But then you have also ones that don't have any common hub, and they use other systems that they depend on, right? CCIP oracles or IBC or some other system. So it's basically the same thing applied to rollups. So that's one of the trade-offs, hub or mesh. Another trade-off is synchronous or asynchronous interrupts, right? Until now, I've been talking about asynchronous interrupts, right? So there's a state transition in A. This is seen in some other rollup. It reacts to it, and then A kind of confirms that the partial state transition did happen on the other side, and it terminates. Another possibility is to just do this the same way Ethereum does, so at once, both or not, right, without that lock on state. or put differently, with a local state only at the level of the sequencers, so whoever is creating the next block. And that's done, obviously, as sharing the sequencer. So having the sequencers of whoever's proposing the next block, let's say, in both rollups, for a period of time, be the same person. And so they can perform the async interrupts, let's say, locally in the different virtual machines that is running. If it's done in L1, this is what is called base sequencing. And we also have examples of the first base sequencing rollup that has been proposed, Taiko. And there's many other discussions around this. It's still a bit raw. But yeah, there's discussion around that. Of course, sharing the same sequencer is more natural if you're doing a hub kind of solution than if you're doing a mesh kind of solution. But I don't think there's a serious proposal of a mesh kind of shared sequencer, but it's not fundamentally impossible. And then, okay, yeah, I'm gonna skip this because I don't have much time. Maybe I can go quickly through this. So this is just to show the trade-offs that exist between the different solutions, right? So the two types of trade-offs that I talked about, whether it's using a hub or using a mesh, and then I differentiate with using L1 as a hub. So what we have by nature, just because we're rollups, is the top row, right? We do async interrupts in L1, very high cost, very high latency. We don't have synchronous interrupts, but we don't have any trust assumption. You can enshrine this with synchronous composability, but it's still very high cost, actually even higher, and very high latency as well. Then the hub, a synchronous type of solution, low cost and low latency. This is common with the mesh. Not necessarily synchronous or composability, but what is better than the mesh is that the only dependency is on the hub being safe. Whereas in the mesh, we have a dependency with every single rollup we interact with. And we need to track this. So we need to track the dependency set of the rollups that we depend on. So if we are happy to interact with rollup B, but at some point rollup B accepts state transitions from rollup C, and we don't trust rollup C, we should actually stop interacting with rollup B. So it gets kind of messy there. Okay. And then one final trade-off. Up until now, I've also been talking mostly about in-protocol changes, right? So you kind of need to do some changes to your code base as a rollup in order to join, in order to be able to understand ACK layer, cross messages, or in order to join a hub, you need to change the rules for exiting your rollup, for withdrawing. But there's also out-of-protocol solutions, right? But for those, we already have a lot of examples. I put some here, like CCIP, Uniswap X has been recently proposed. This is mostly, I think, for token transfers, and there is still a risk, but it's not at the protocol level. The risk is taken by the liquidity provider, right? So whoever is willing to take the risk of an equivocation attack can charge some fees to the user and just give some, let's say, risk-free tokens and take the ones that are still subject to a safety attack and disappear. And one final option for a rollup, which has not been proposed yet, but I think is a very interesting one, is a hybrid-based rollup. Because the good thing with base rollups is this option to first credible neutralities. So it's in protocol, but the protocol that we're relying upon is Ethereum, so we're already relying on that. And we also provide synchronous composability with L1, but the cost is too high. But you could do something like, let's become based every once in a while. We can track in a deterministic way demand for this, and let's say every 10 slots we become based, but the other 9 we operate in our own way because most of our transactions do not actually need this, but whenever they need it, we become based. So they're still, it's still very open, especially everything about shared sequencing is still very much raw, and there's a lot of space for proposals there. So yeah, in general, every rollup needs to make compromises and decide its vision. Personally, I'm trying to push for a hub kind of solution internally, tracking development and contributing to shared sequencing and base sequencing. And in my opinion, the vision, I think what's gonna happen is small rollups are never gonna be part of the dependency set in a mesh type of solution. So it's only natural that small rollups are gonna join bigger hubs, and then maybe between hubs they're happy with, depending on each other, because the chances of them causing us a safety attack are much lower. But a small rollup is never going to be accepted as a dependency for bigger rollups, which is the same thing that happened on L1s, right? we have multiple L1s and they interact with each other through some services that are willing to take risk because the L1s are big enough for these services to exist. So yeah, that's in conclude the presentation because I'm out of time. But thank you. And if you have any questions, let me. Happy to answer.
Thank you, Alejandro, for the nice talk.